class, today's day 2 of inverse functions, lesson 5.1.2. The topics that we're going to cover are inverse functions on a coordinate plane, algebraically finding functions inverses, which we did last time, domain and range with respect to inverse functions. Okay, we're going to do this example first. Okay guys, so again, umpteenth time I'm recording this video. Yesterday we learned about the definition of inverse functions, and we learned that the x and y values switch for the points. Today we're going to look about what happens with inverse functions on a graph. So you can see right here we have this function, it's a line. The equation here is right here, y equals 1/2 x plus 3. As you can see, I'm turning it on and off. So this is the line. I've got a couple of points on this line. There's the point -6, 0, -4, 1, 0, 3, 2, 4, and the point 8, 7. What we're going to do is we're going to switch all these x and y values, and we're going to plot those points. So here they are, right here, -6, 0 is 0, -6, -4, 1 is 1, -4, and so on. So plot all of these points here. So 7, 8 is the last one. And we're going to draw a line through these points. So, and then you can see that line is this equation, y equals 2x minus 6. Okay, so it talks about this a little bit, if you could see on your homework questions, but basically, it doesn't look like there's too much, with just lines, it doesn't look like there's too much a relationship, but there is a relationship. These are reflections over each other. They are reflections of each other over this line, the line y equals x, the line with a slope of 1 through the origin. And I'll show you just in a second how that is. So if I take away this line, and so this program is pretty cool. I can do reflections. You see it says reflect about a line. So you select object to reflect and then the line of reflection. So I'm going to reflect about a line. So I'm going to select this line, and I'm going to say I want it to reflect over this line. And if what I was saying is right, then yes, this line shows up. And you can see it is exactly the same as these equations. So this reflection, right, indicated by f prime, right, this is a reflection of f, is the same as the inverse function. So yeah, let's look at some more examples. My bad. Other function here, this time this is a parabola. As you can see, it has this equation, y equals 3x plus 2 squared minus 6. Right here, our vertex must be -2, -6, right? The opposite of this one and the same as this one, right? -2, -6, right? Which is this point here. That's flashing. And then we have a couple of other points. We've got on here, we've got -4, 6, -3, 3, -2, -6, and 0, 6. So we're going to do the same thing, right? We're going to plot the inverses of all of those points. So we're going to plot -6, -4, -3, 3. Nothing really happens because they're the same coordinates. -6, -2, and then 6, 0. And you get this sideways parabola. So again, the question is, graphically, what is the relationship between this original function and its inverse? So like I said before, they are reflections of each other. They are reflections over this line, right? So right? So if you fold this original parabola over this line, you get this sideways parabola. Okay, and let's do what we did last time. So let's take this away, and then I'll show you reflection. So go reflect about a line, you select the object to reflect, and then the line of reflection. So we're going to pick this parabola, and we're going to say reflect over this line, and then there you go. You can see, let's adjust this a little bit. So you can see the reflection, C prime, is the same equation as that sideways parabola that goes through these points. So again, the inverse relationship is a reflection over the line y equals x of the original function. Alright, one more example. Last one of these examples, this time we're going to deal with a cubic function. The equation here, so this function that I'm turning on and off, right, is this equation, 6x cubed minus 13 over 6x plus 2. If you recall, like, parabolas, right, they kind of have one hump, you know, like this one turn, as you can say. Cubics tend to have about 2 turns. So anyways, we graphed also these points on this cubic function. We've got the point -4, 0, -3, 4, -2, 5, 0, 2, 1, 0, 2, -1, 3, 0, and 4, 4. So again, we're going to graph all the inverses of them. We're going to graph 0, -4, 4, -3, right? The flipped version of -2, 5 becomes 5, -2, then 2, 0, which is flipped of 0, 2, 0, 1, -1, 2, 0, 3, and 4, 4. And then if you draw a curve through all of those, you get this curve here. This equation is very complicated. It's called a parametric curve. It's very hard to solve. We'll get to why it's difficult in the next couple of problems, but for now, I only care about if you notice that this is a reflection of the other graph. So again, if you draw the line y equals x, right, so with the slope of 1 through the origin, and you reflect this cubic, you should get that same shape that we had drawn here. Okay, so let's do that again. So we're going to reflect about a line, so we're going to reflect this cubic over this line, and it should, that same curve should show up through all those points, right? And it does. Let me change the color here so it's not the same as the other one. Okay, so you can see this is the same as this one, right? So these are the same exact two things. So this is a reflection of the blue function, the blue, or not a function, but the blue relationship between all these points, right, is the inverse relationship of this cubic. You can see it. You fold it along this line y equals x, right, they land on top of each other. So that's it. Last one of these examples, this time we're going to do. Okay, so now we're going to get into what I was talking about, how that cubic function had like a weird equation for the inverse and stuff like that. We talked about how the graphs of the functions, right, are the reflections over the line y equals x. So if you have an original function, its inverse is a reflection over the line y equals x, right? We're going to get into why it was a weird function. And that has to do with the domain and range of the original function and its inverse function. So we're going to focus on this parabola, y equals x over 2 squared. And so we have this, and we know, let's find its inverse, right? So we want to draw the line y equals x, right? So here's the line y equals x, and we're going to reflect this parabola over this line, right? And then we get this sideways parabola, x equals y over 2 squared, right? So the inverse obviously is the same equation, right? Y equals x over 2 squared, but the x and y are switched, x equals y over 2 squared. So there is our original function and our reflection of the original function over y equals x, which is our inverse equation. Okay, so now I'm going to ask you, what is the domain and range of the original function, and what is the domain and range of the inverse? Okay, you're right. So the domain of the original function is all real numbers, where I can widen this as much as I want. It goes forever out. And the range is higher than, its y is greater than equal to 0, because the lowest point here of y is 0, and it goes forever up. So it goes forever up and out. Interestingly, so the domain is all reals of the original function. The range of the inverse is all real. So the domain and range switched. So the domain was all reals, so now that's the inverse's range. And the range of the original function was y is greater than or equal to 0. The domain of the inverse is x is greater than or equal to 0. So the domain and range switch for original functions and their inverses. Okay, next question I want to ask is this inverse a function? Yes or no? Okay, so it is not a function. That is because it doesn't pass the horizontal line test. Remember, if you draw a horizontal line, so let's just focus on this. So this is not a function, because if you draw a horizontal line, right, if it hits at any point more than once, as you can see, it hits twice, right there, then it is not a function, right? Unlike the parabola, if you draw a horizontal line, it only hits one time. So the parabola is a function, however, its inverse is not a function. So this is important. So let's focus on just the positive part of the original function. So here's our original function. Let's focus on, let's trace just when x is positive. So if x is positive, sorry for the delay, folks, then you just get this part, like this half upwards parabola. And then the question is, if you restrict the domain to just when x is positive, will this now, if you reflect it over the line y equals x, if you create an inverse of this, will you get, so if you reflect just this part, will you get a function? So if you reflect that, you get this, y equals square root of 4x, and this is a function. Okay, and then that's going to bring us more, we're going to talk about that some more tomorrow, but like basically which functions have inverses that are functions which functions have inverses that are not functions. So this parabola has an inverse, but its inverse is not a function. But if you restrict its domain, as we said, to just that inverse is a function. So there are some functions where their inverses are also functions, and some functions where their inverses are not functions. Okay. Okay, I want to apologize for the last side. I kept saying vertical line or horizontal line when I clearly meant vertical line. So I apologize for that. Horizontal lines are on my mind, and you'll see why. Also, from the last example, we talked about how that parabola, its inverse was not a function. That sideways parabola, as we know, is not a function. It does not pass the vertical line test. When we restricted its domain to just positive x values, that produced an inverse that was a function. So let's figure out, when is an inverse a function? So we're going to go over all the examples that we've done already, and then one new one. This is the first example that we did with a line with a slope of 1/2 and a y-intercept of 3, y equals 1/2 x plus 3. Its domain is all real numbers, and range is all real numbers. And this was its inverse. It had a slope of 2 and a y-intercept of 6. Its equation was y equals 2x minus 6. The domain and range, as we've said, it switches when you have the inverse function, but since the original function, the domain and range was all reals, it doesn't really look like it's switched, but it has. And this inverse is a function, right? So that was a situation where you found the inverse, and the inverse was a function. This is the next example that we did. We did a parabola. The equation was y equals 3 times the quantity of x plus 2 squared minus 6. Right, it had a vertex of -2, -6. Its domain was all reals, and the range was greater than or equal to -6. When we found the inverse, right, we found this sideways parabola. Okay, and this is more obvious when the domain and range switch. So the domain of this one is greater than or equal to -6, and the range for this one is all reals. However, sideways parabolas are not a function, so this inverse is not a function. Okay, let's look at the next example. The next example we covered was this cubic. Its domain and range is all real numbers. And when we found its inverse, right, the reflection over y equals x, we got this curve. And again, the domain and range switch, but it's not obvious because they're the same. The domain and range for this curve is all reals as well. But this inverse is not a function, again, because this does not pass the vertical line test. And at some points, the vertical line can hit 3 places, right? So it can only hit once. All right, let's look at our last example that we did with the restricted domain. So here's the half parabola with the restricted domain where x is only positive. The range also is all positive numbers, including 0. And when we restricted it, right, we got this square root function. Right, and we said that now it is a function, right? The domain is in range, it's switched, but they look the same, and this is a function. Okay, let's look at a new example. It's this exponential function. It has an equation of y equals 2 to the x. Its domain is all real numbers, and its range are greater than or equal to 0. And when you find the inverse, right, the reflection over y equals x, you get this graph. The domain and range switch, So the range was y is greater than or equal 0. Now that's the domain, and then now the range is all real numbers. And this is a function. It's actually called a logarithmic function. We're going to be learning about them next week. Okay, let's focus on the functions that did have inverses that were also functions. So it was these three. So the line had an inverse that was a function, the half parabola did, and this exponential function. So what do all of these functions have in common? What makes these functions have inverses that are functions, and what makes the other ones not? Okay, these functions, let's focus on these. So here they are. These functions are called one-to-one functions. Okay, so one-to-one functions, the definition is for every output there is exactly one input. Okay, and so you'll see why I kept saying horizontal when I meant vertical, because there's another thing called the horizontal line test. So if a function is a one-to-one function, it passes the horizontal line test. Okay, so what does that mean? Well, if a function passes the vertical line test, which you've known from way before, then the relation is a function. So, right, parabolas are functions, cubes are functions, they pass the vertical line test. But will their inverses be functions? If a function passes the horizontal line test, then its inverse is a function. So these ones pass the horizontal line test, because when you draw a horizontal line, when you draw a vertical line through them, they're functions, and a horizontal line, it only hits once as well, so that means their inverses will be a function. Okay, so let's summarize what we've learned up to. So, the last lesson, we talked about the definition of an inverse function. An inverse function is a function that undoes the operations in the original function. If the point xy is on the original function, then the point yx is on the inverse function. And the inputs of the original function are the outputs of the inverse, and vice versa, right? The inputs and outputs switch. Okay, inverse function notation, right? If g of x is the inverse function of f of x, then g of x can be written as f inverse of x. And then the last thing that we learned yesterday were about undoing equations. To solve for the inverse function, you switch x and y for the original function, and then you solve for y using inverse operations. Okay, what else have we learned about inverse functions? What's new today is inverses on the coordinate plane. So we learned that inverses are a reflection of the original function across the line y equals x, right? So if you reflect the original function across that line, you'll get its inverse. And we learned about domain and range with respect to inverse functions. The domain of the inverse function is the range of the original function, and the range of the inverse function is the domain of the original function. So if the original function passes the horizontal line test, then its inverse is also a function. So I apologize for this late video. This has been a complete nightmare. I hope you appreciate the hours and hours that I put in to put this video. Okay, thanks.